One more property that we need to talk about is the length of a curve. So imagine you have we're doing our usual abuse of notations. We have some curve gamma. This curve is parameterized by some function gamma of t. Then the length of gamma, it turns out, will be given by, let's say this is parameterized by gamma of t, where t goes from a to b. Then the length of gamma is going to be the integral from a to b of the magnitude of gamma prime of t dt. Okay, and so this is actually a fact that you've seen before, namely in Calc 2. So this is when you talk about arc length, this is basically the arc length formula. Here are arcs or our curves. Okay, so nothing really too mysterious here. Let's do just one example, and then we'll have one consequence, one place where this length kind of shows up for properties of integrals. So let's look at gamma. Let's let gamma be the circle of radius r. So let's let gamma denote the circle of radius r. Notice that the orientation actually is irrelevant here, but it's a circle of radius r. Then gamma of t is going to be r e to the it, where t goes between 0 and 2 pi. And then the length of gamma is going to be the integral from 0 to 2 pi of the magnitude of gamma prime. So if gamma of t is r e to the it, gamma prime is going to be r I e to the it dt. And let's think about this. This will be the magnitude of r times the magnitude of I times the magnitude of e to the it. And the magnitude of r is just r. And the magnitude of I happens to be 1 because that's distance 1 from the origin. And actually the magnitude of e to the it is also 1 because that's a point on the unit circle. And so that's also going to be distance 1 from the origin. So this is just going to be the integral of r from 0 to 2 pi dt. And that, of course, is just 2 pi r. So we get the usual fact that the circumference of a circle is 2 pi r. All right. It's always good that prior facts, agree with new methods. The property that I wanted to talk about, so we can call this a proposition if we like. This is just one more property that integrals are going to have. And this is kind of an integral. If you think about it, it's in a certain sense an integral analog of the triangle inequality. So what this is going to say is that if you integrate a function, say f of z dz over some path gamma, then that's going to be less than or equal to the largest value that the function takes over that path. It's going to be the less than or equal to the maximum of f of z, where z is in gamma, times the length of gamma. So times the length of gamma. This is kind of like in Calc 1 when you integrate. So I guess instead of thinking about this as the triangle inequality, which it still is in a certain sense, but maybe a better analog is actually to think about when you have a function, you know that the function is going to be, the integral under this function is going to be less than or equal to the largest value of the function times the width times the length of that interval, right? So you know that the integral, which is this blue part, is going to be the area of that blue part is going to be less than or equal to the area in the green box, right, which is the largest value times the width of the interval. So I think actually that's a better analog for what's happening here, but this is another property that that these complex integrals are going to have.